calculus students. So here's my video for the notes on continuity. If you need to take a minute to review the notes that we already took in class, go ahead and hit pause and do that. Otherwise, I'm going to get started. So the final notes that we took in class were about these properties of continuous functions. And these properties apply when we are thinking about whether functions, algebraic functions, are continuous or not. So if we know that f and g are continuous, we know that all these other operations involving f and g are also continuous. So we're going to look at some examples of that. So this first example, we have y equals the absolute value of x minus 1. So I can think of y as a composite of two functions. I can say y is a composite of f of x equals the absolute value of x and g of x equals x minus 1. Okay? So f of x is just an absolute value, a basic absolute value. We know that's continuous. G of x is just a line. We know that's continuous. So since f of x and g of x are continuous for all real numbers, so reminder and notation, this means all real numbers, then we know that f of g of x, which is equal to y is the composition of those two, is also continuous for all real numbers. Okay. So the directions were to find points of continuity and discontinuity and identify each type of discontinuity. I stated that it's continuous for all real numbers, which means that there are no discontinuities. Okay. Cotangent. So just a reminder of cotangent. It's the reciprocal of tangent, which I think I talked about the other day in class. So we have pi and 2 pi. And the graph of this kind of goes like this. Like that. And there are asymptotes right here. Okay, so we can clearly see that these asymptotes, they represent infinite discontinuities, because infinite discontinuities are when the left and the right side goes to positive or negative infinity. Okay, so we'll say that cotangent of x has vertical asymptotes at x equals, and I'm going to write an equation for it. So I can see that it's all the x values that are factors of pi. So I will say x equals k times pi when k is an integer. Integer just means whole number. So if k is an integer, then all the asymptotes are at x equals k times pi. So this would be 1 pi, 2 pi, 3 pi, negative 2 pi, negative 3 pi, etc. Okay, so since there are vertical asymptotes there, we can say, so cotangent of x has infinite discontinuities at those points. So cotangent of x has infinite discontinuities at x equals k times pi. So I found the point of discontinuities and I identified the type as infinite discontinuities. Cool. Okay, and one last example similar to this with a piecewise function. So example 3 says, find each point of discontinuity and then determine which are removable and which are not removable. So if you need to pause and go back and determine what removable and not removable mean, go ahead and do that. So what's a removable and what's not removable? Okay. So when you have a piecewise function, in order to determine if it is continuous, remember we should follow those same steps that we did before with our graphs. So what determines if a function is continuous? It has to meet these three criteria. So the limit must exist, and f of c must be defined, and they must be equal to each other. Okay. So I can really quickly look at this, and I notice that f of c does not exist, because here our c would be 2. So we're looking to see if it's continuous at 2, because that's where they might not be connected. And I can see that since f of 2 is undefined, since f of 2 is undefined, then we know that x equals 2 is a point of discontinuity. Okay, so since f of 2 is undefined, because we're never told what happens when x equals 2. There is no x equals 2. There's no value for when x is equal to 2. So this is a point of discontinuity. And then in B, we have to figure out, is it removable or not removable? So looking back here, we're either going to have this case of a jump or this case of a removable. And so what we need to look at is, are the limits from the right and the left equal or not equal? If they're not equal to each other, then we have a jump. If they are equal to each other, then we have a removable discontinuity. So we're going to determine the limit from the left and the right. And I'm gonna state that. So determine if f of 2 is removable discontinuity or non-removable by comparing the left and right limits. So we're going to compare the left and the right limits to determine if f of 2 is a removable discontinuity or non-removable discontinuity. So let's look at the limit as x approaches 2 from the right. And if we're looking at the limit as x approaches 2 from the right, that means the x values are bigger than 2, which means we have to use this equation. So I'm going to use x divided by 2 plus 1. Okay. So I can just plug in 2. This is equal to 2 divided by 2 plus 1, which equals 2. Then the limit as x approaches 2 from the left. From the left means we need x values smaller than 2, so we're going to use this equation. And so this equals 3 minus 2, which is 1. Okay. So since the limit does not exist, the left and the right limits are not equal to each other. So we can say, since the limit as x approaches 2 of f of x does not exist, then the discontinuity at x equals 2 is non-removable. Removable. Okay. Okie dokie. let's move on. So we're actually, I think the pages got flipped. We're going to move on to this page with the blank at the top. Okay. Okay. So if a function has a removable discontinuity, we can write what's called an extended function. We can write an extended function that is continuous at the point of discontinuity. Okay, because if you think about a removable discontinuity, it's really, really close to being continuous. So we have the limit. We just basically would need to fill in this hole. And that's what an extended function is. It's a function where we add that value that would fill in the hole to make it continuous. So we're basically adding to the function. We're making it a piecewise function to make it a continuous function. Okay, so let's look at an example. So give the formula for the extended function that is continuous at the indicated point. So we want to make it continuous at x equals -3. And the reason why is we know that f of x is not continuous right now, since f of -3, if we plug in -3 here, we get undefined. We get 0 over 0. So this is undefined. Okay. So we want to make a formula that will make it continuous at that point. Okay. This one's kind of basic. A lot of you might already be seeing what we can do with this equation. We can factor this thing. So I hope your instinct was to factor that. I'm going to call our extended equation e of x, and I'm going to rewrite it, factoring. That would cancel out, and I'd be left with x minus 3. So x minus 3 is the extended function that does make this continuous at that point. Okay? And just so you can kind of get a visualization of this, I'll open up decimals. And show you what the graphs of both of them look like. So our original f of x was equal to x squared minus 9 divided by x plus 3. And you can see at x minus 3, it's undefined. It's undefined. And then our extended function was just x minus 3. Oops. X minus 3. What am I doing wrong? Why does that look like that? X minus 3, there we go, okay. So I'll just write x minus 3. So then we can see when I go to -3 here, now I have the value -6. So they're very similar. They're the same thing, except the red graph has a hole here. It's undefined. And the blue graph is extended so that it is continuous at -3. Oops, I'm still looking at the red graph. Go away, red graph. The blue graph is continuous at -3, right there. Okay. Let's look at a little bit more challenging problem. So f of x is equal to sine of 4x over x. Okay. So when x equals 0 in this initial graph, we know that we get 0 over 0. So again, f of 0 is undefined. Gasp. But we can change it using those tools that we have to write an extended formula that is continuous. Okay? So this is where we're actually going to write a piecewise function. So what we would need to do is figure out what hole do we need to fill. We need to figure out what is the value of that hole. So we know that f of 0 is undefined, but we want to know what should f of 0 be to fill the hole. And the way that we're going to do that is we're going to figure out what is the limit as x approaches 0 of sine of 4x. Okay? So this will tell me where is the hole and what is the value that the hole should be. So we need to solve this using our special trig limits. I'm going to multiply the top times 4 and the bottom times 4. And when I do that, I can see right here is my special trig limit, and I'm left with this extra 4 outside. And so my special trig limit goes to 1, and so it's 4 times 1, which is equal to 4. Okay? So what this is telling me is that when x is going to 0, the graph is going to 4, but we have a little hole there. So let's look at this again in Desmos. So when I have f of x equal to sine of 4x divided by x, at 0, it is, come on, maybe I have to zoom in a little more. At 0, it is undefined. See? There's the hole. But we know that the graph should be going to 4. And so what we need to do is just fill in this hole. And what this is going to look like is a piecewise function. So I'm going to make my extended function, e of x, a piecewise function, where we still have that original graph, but only for when x does not equal 0. So we still have the original graph, but only when x does not equal 0. And then we just want the function to be 4 when x does equal 0. So what this is doing, it's keeping our original function, but then adding this point when x is 0, the function is 4. So what that will look like on Desmos is basically I'm adding the point, I'm adding the point 0, 4. And see, the hole is filled. So now this is a continuous function. The red graph is undefined there, but the blue graph fills that hole. So right there, it fills the hole. So this would be the extended function that makes it continuous at 0. It's a piecewise. Okay, we're going to do one more problem together. We'll do example 5. Example 5 is probably the most important example. You will definitely see stuff like this on the AP exam. So pay careful attention. So example 5 says find the value for k so that the following function is continuous. So we want f of x to be continuous, and we need to figure out, okay, what does this k value need to be so that it is continuous? Okay? So in order to be continuous, we know that the limit from the right and the left have to be equal to each other. So what I'm going to do is I'm going to figure out, okay, what's the limit from the left so that I can make this limit equal to that value. Because I can find the limit from the left. The limit as x approaches pi from the left, we will use this top function, sine of 2x. And this is equal to sine of 2 pi. And sine of 2 pi is equal to 0. So if the limit from the left equals 0, then I know that I want the limit as x approaches pi pi from the right of f of x, I want that also to be equal to 0, so that this is continuous. Okay? So the limit as x approaches pi from the right would use this bottom function, so that because those are x values bigger than pi. So of 2x plus k equals 0, and I will just substitute pi in for x. So 2 pi plus k equals 0, which means k needs to equal negative 2 pi. So that is the value of k that will make this function continuous. Okay. And I mean, you could also check, oh, we need to make sure, does f of pi equal 0? Because that would also need to be true, just to check, make sure all our rules of continuity are in check. And yes, that's true. So if I plugged in pi to my function, I would have sine of 2 pi, which equals 0. Yay. It's definitely continuous, and this is the value of k that will make it continuous. Okay. So what I want you to do, I want you to do one problem on your own. Come to class with this you try problem down. It's the same thing that we were just doing with example 5. So it's kind of a continuation from example 5, but I want you to try that on your own. So come to class Monday with this completed, or at least attempted, and you can bring any questions that you have then. I hope you enjoyed my YouTube video. Please like and subscribe, and have a great weekend. Bye.